saying. Okay, so today I'm going to answer questions about the dice lab, if you guys have it, for the dice stats. The only method we need to make our average, the method you are required to make is the dice rolls. You need to have a method that can accept some kind of number, and it's going to roll the dice for you. So essentially, basically, you're just writing a method that generates a random integer between 1 and whatever number you give, including 1 and that number. Remember we talked about last week, by default, the random.nextInt is not inclusive. It includes the lower bound, but it doesn't include the upper bound. So you need to look up some stuff of how to work around that to make it work for you. What else was I going to say? As far as the standard deviation and calculating the average, you can delegate those to methods, and I would encourage it because those are like sub-tasks that you can give to methods to do. So yeah, having those be methods might be a good idea, but you're not required. Any other questions? By the way, if you guys don't want to type it out, you can always just unmute yourselves and ask. Yeah, that's a good mentality to have. Just audit your main method and be like, okay, how can I make this a little less dense? And sometimes you can't necessarily do it. One of the things that helps limit code the most is learning how to write classes, because now you can really just split your code apart and designate other tools to do a bunch of other stuff. But for these methods, for these labs, sometimes it's not possible to really condense. And I'll review my dice stats lab. I'll go over it next week and I'll show you what I wrote. Mine isn't exactly super trim either, I don't think. Let me check what I wrote. Yeah, my main method is also got a lot of stuff, but that's because I made like 6 different arrays. It is possible for you to do this lab making just one multi-dimensional array. I have a few students who've done that. If you did that implementation, that is fine. Yeah. Any other questions about the dice stats lab? They specify another. Your whole output will display the stats for the 6 different types of dice there are in tabletop role playing. So that is the D4, the D6, D8, etc., all the way up to D20. Is there any user input? No, it's just a simulation.
I have a quick question.
Sure.
So when you showed us the example output, mm-hmm. What was the number of dice rolls? Like, what was it?
10,000 rolls for each.
And that was what you had in your output? You had that much of a difference in the thing?
Yeah, I mean, my output is my output. So
okay. Yeah, because whenever I set it to like 10, I get like 9 to 20% percent error. But when I set it to 10,000, the errors get really small.
Yeah, that's actually expected. That's why you take really large samples when you're collecting data. Okay. Because smaller sets of data, and you'll learn more about this when you get to statistics and even like physics, if you guys are taking physics lab this week. If you have a smaller set of data, it's more variable. It's going to be very big difference between each data point. That's just how it works. But when you get to bigger and bigger sets of data, you're going to be approaching the theoretical thing more. Like for instance, that physics lab I talked about where you measure the gravitational acceleration due to gravity by like taking an object and just dropping it and using a photogate to measure its speed, just basically measuring like how much time it took to pass like between point A and point B. And you can do a bunch of math with physics formulas there to figure out the acceleration due to gravity. If you only take 5 samples, chances are your data is going to be very different, and you're probably not going to be that close to 9.8. You're going to be like at 10 point something or like 9.6. It's going to be really weird numbers that don't go with what you expect. But if I were to do it 100 times, then my numbers are going to become a lot more closer to 9.8. That's just how data sampling works.
Yeah, I got the same as you, Matthew. It was getting really close to 0. Like every time, I kept redoing it to see if I could ever get like a high error percent. But I really wasn't getting high ones.
Yeah, that's why it's nice to have your number of roles set aside as a constant. So if you just wanted to like play around with it, you only have one place to change. You don't have to go to like 8 different places in your code and change the hard code to 10,000 to be whatever else you want it to be. That was another goal of this lab, is to teach you guys to start putting your constants into final variables and start kind of be thinking about your code in that regards, because that's going to be something very important. You're going to thank yourself later in the future. Because if there's just a bunch of hard-coded values here and there, it's going to be a pain in the ass to go through and spot all of them, especially when you get into complex projects that have a bunch of different files that use the same constant. Notice my stats stay the same every run. That's also possible. Again, when you have a big volume, the output, the general stats won't change that much. But if you, Mato, if you were to take your run, if you were to take your max number of rolls down to like 5 or 10, then your stats are going to change wildly between every run of the program. But yeah, that's just, again, that's just like data collection, sampling stuff. I'm sure when you guys get to statistics and your physics lab, your instructors will tell you the same thing. Any other questions about that lab?
I was kind of thinking of using a 2-dimensional array, but I don't think that would have worked, right?
No, it would work.
Right. Oh.
And we'll talk about what 2-dimensional arrays are here today. So if you wanted to go through your lab and instead of having 6 different single-dimensional arrays, you could have one multi-dimensional array.
Okay, because I also coded like multiple lines of the same thing, I want to say.
You'd have to be more specific on what that is. Yeah, I know you're not trying to give it away, but
yeah. Well, I did multiple for loops to what's it called, assign values to the different arrays.
Yeah, that's what you'd have to do. I mean, my code is exactly like that too. Using strictly single-dimensional arrays, it gets messy. You can make this code way neater by using a multi-dimensional array, and that's probably something I'll demo when I go over the dice stats lab.
Yeah. Oh, okay then.
So let's get into today's topic, which is multi-dimensional arrays. I know most of you probably covered this last week. If you have any, let me pull up the chat too. If you have any questions as we go about multi-dimensional arrays in general, things that you didn't understand from your 210 classes, feel free to shout it out, and I'll do my best to address them. Let's go ahead and actually clear all of what I wrote from the last class. By the way, one thing I'm going to start doing is I'm going to, for some reason, Zoom is not letting me record to the cloud. I don't know why. I'm trying to debug that problem. And I know it's a pain in the ass as a student to, like, when your instructor puts up a recording, having to download it and watch it in like your local media viewer. So I'm just going to start putting them up on, YouTube as unlisted links and share those. So until I figure out how to record back to the cloud, that's how the links for the lecture replays are going to work for this class. Okay, so, excuse me. What are multi-dimensional arrays as a definition? So first off, what is a single dimensional array? What does an array do in general? What do we use arrays for?
The collection of elements with the same data type.
Exactly, that is precisely what it is. So let's say we had, so that definition is very broad and can apply to variables as well. Arrays specifically hold multiple values of the same type. We use them to solve problems. That is, you can apply that to everything, but I like where your head's at. And my array is equal to, so there's 2 ways we can initialize an array. One, we can just do it like this, new array. So what this says is we are creating a blank array of ints named my array with a length of 5. That's what's happening here. Down here, we are just assigning over here, and I'll actually put the comment above, over here, we are 2, 3, 4, 5. Array initializer allowed here. The initializer like this. And I'm just going to comment that part out. Here we are creating a new array of ints named my array initialized with the given values. Okay. That's how we do it for just a single dimensional array. And how do we know how many dimensions an array has? So let's look at a 2-dimensional array. My 2D array. What are some things we notice immediately about this declaration?
The 2 brackets.
Yeah, 2 brackets. What conjectures can we make about what that means? What do you guys think that might mean?
The first bracket, inside you would put, it's basically the rows and the columns.
Yeah, exactly. For a 2-dimensional array, that's a very good way of thinking about it. It's the rows and the columns. I'm going to show 3D array, and when we get to 3D array, the distinction. So, okay, multi-dimensional arrays are actually arrays within arrays. And I'm just going to initialize a blank one here. We'll just say it's 3 by 4, let's say. What actually ends up happening here is this is what my 2D array actually looks like. So my 2D array is an array, and inside of it, there are 3 arrays of length 4. So within, we have 1, 2, 3, 4 elements, and we have 3 of these. So we know that in here we have indices 0 through 3, and the outer elements are indices 0, 1, 2. And if we think about it in the rows and columns method, 2, 3, right? We got our rows over here and our columns over here, row, column. But in a concept I'm going to illustrate now with a 3D array, my 3D array, so if it's a new integer 3 by 4 by 5, I'm going to go to the whiteboard to draw this out. Let me share whiteboard. So we have an array here. I'm just going to call it my 3D. It's equal to 3 by 4 by 5. That's not a good color. 3 by 4 by 5. So if we actually dissect this, we have an empty array. So here's our main array. This is my 3D array, this big giant array over here. And inside of it, we have 3 subarrays. 1, 2, 3. And inside of each of these arrays, we have, inside of each of these subarrays, we have subarrays. And we have 4 of them. I'm just going to do it just for one. 1, 2, 3, 4. And each of these subarrays are themselves an array of length 5. So I'm hoping with the colors, it's a little bit more clear the concept I'm trying to get at. Let me know if you guys have any questions. I'm trying to formulate a different way to explain this as well, in a way that's not as confusing without as many terms. Again, does the concept of a multi-dimensional array is an array within an array, is that kind of registering just from this? Are you guys kind of seeing how that works?
Yeah.
On the participants window, give me a thumbs up if you totally got it, thumbs down if you're totally lost, and a clap if you're kind of halfway. Alan, do you have a question?
No,
Okay. Oh, I got you. Okay, so most of you are getting it. A couple of you are halfway. Those of you halfway, what kind of questions are, like, what's kind of, what would help you more? More graphics like this, or maybe like an example? Like me printing out an example of a 3D array. In what situation would you use a 3D array? Matthew, that kind of depends on your problem. I said this to the last class as well. One of the things, our goal here is to tell you, hey, you have these tools and here's what they do. We'll try to come up with some examples, but it's really hard to come up with an example like this. That's such a specific solution that won't be contrived. An easy example is suppose you had a program where you asked the user for you wanted to, I don't know, store like the lengths, widths, and heights of three-dimensional objects, and you had a my3D array of length 111, and that's how you stored the values. That could be one example, but then you could also argue, why not just use an object for that? It's hard for me to answer that question because there isn't like a clear-cut example, but understanding how these work will kind of help you better visualize if one day in the future someone throws like a 6-dimensional array at you, you just know that that's a list within a list within a list. Oh, here's a good example. Actually, who's familiar with JSON requests? Who has ever heard of what a JSON response is? Sorry, a JSON response. Okay. A JSON, I'll go back to code for this. A JSON response, or a JSON, is just a formatting of data. It is a very easy way for us to create what's called key value pairs within our data. So suppose is often used, does 6 look like? Well, they're arrays within arrays. So really 6 dimensions is not like within physics of 6 dimensions. It's just 6 levels of embedded arrays, right? Yeah, exactly, Anthony. Suppose we have imagine we have a table of data, and this data holds the user's name, their email, their phone number, and let's say they have a list of their favorite foods, okay? Now let's model what that would look like in a JSON response. So we'd have and we have multiple users as well. So for each user is a collection of data, right? Because if we have a table with multiple columns, each user is a different row in that column. So right here, we know we're gonna have multiple arrays for our multiple users. Each user has data, their name, and then the data goes in here. And then they have their age, data goes here, their email, data goes in here. And then we'll have, say, their favorite foods, okay? And because they're gonna have more than one favorite food, probably, we make that as a second array. So, he's gonna be like A, B, C, D. Let's say these are their favorite foods. And this is the data for one user. We repeat this for multiple users. So we'll have John, he's age 22, email is John. And then,
Wait, can you store that in a 3-dimensional array, even though the type is int?
Yeah, you could. Instead of making it an int, you could just make it a string and save it as a string. Then use Java library stuff to convert a string to an integer.
Yeah, I was just trying to make sure you can't be putting int arrays inside of string arrays inside of other types of arrays. I was like, nah.
No, yeah. I suppose this is all string. So let's say let's model this actually. Let's model this. String 1, 2, 3 user data is equal to new string, and let's say we can hold up to, I don't know, we can hold up to 10 users. Each user has 1, 2, 3, 4 different fields of data, and then they can have up to, say, 5 favorite foods, right? So if we wanted to put John in here, we wanted John to be the first user, we could say user data 0 equals, we got a list here of John 22, John at John. Then we'd have a second array over here of A, B, or we'll just name some foods, right? Cake, burger, pie, fries, and apple. Okay. And so there, array initializer is not allowed here. Damn it. So then we would maybe say like, we'll call this like string John's food. This is kind of tacky code because I'm just, you know, doing it on the fly. And John's food. Oh, sorry. Does that work? Yeah, that should work. Why aren't you working? But I do have a, this is, sorry, I'm trying and failing. Where am I missing the semicolon? What? Help me out. Why am I not seeing it? Apple, burger. Right, so let's just say that. Is there another? Oh. Each of these has to be its own array.
Well, yeah, I think that's what it is. I think you're supposed to, like, aren't you like kind of like writing the array in? Aren't you supposed to use the curly brackets? Or?
That's when you initialize it. Here we're not initializing it.
Oh, okay.
Here we're just defining what it is. Okay, fuck it. We'll just define it on the fly here. I mean, I'm just gonna say this is just like one user's data. Oh, here we can try to make multiple users' data. So one of them is John. These all have to be their own arrays. John 22. John and John. And then I have another array over here. Apple. Burger. Why are you doing this to me? Burger and pie. And basically here, we've converted a JSON response into a multidimensional array. Now, normally you wouldn't do this. There actually exists a JSON class in Java, but this is just to show you that this is something you can do. Oh, you are correct, Juvenal. That's what I was supposed to do. No, because in their original thing, like this outer one was all of our different users. So thank you for actually mentioning that. So we can have a separate user here whose name is Kathy. Kathy is, let's say, 12. Kathy at Kath. And her favorite foods are, I don't know, Butterfinger and peaches and apples again. So right now, the dimensions for this array would be the lengths, because we hard define that would be 2 by 1, 2, 3, 4 by 3, because both of these arrays are only 3. Now, if I added another thing here, like chocolate, then this would become 4. Because the length is the max number of elements you can have, not how many there are. That is an important distinction to make. Whenever you query the length of an array, let's say you have an array of length 6, but you only have 2 elements within it, that array.length is going to give you 6, not 2. Because the length is a query of the max size of the array itself, like how much memory space is, how many slots of memory are allocated for this, not how many elements it has. That's something you have to check on your own. So it is possible to have arrays with elements less than the length, but you can never have more elements than the length because that's how you get errors. Okay, here we just crazy thing where we turn JSON to multi-dimensional arrays. In the old definition, okay, so kind of where we have to like let it go is the definition of it changed, basically, the size definition. But yeah, because this is 4, or sorry, yeah, because this would be like 4 inside, you can have 4 names. You can have 4, up to 4, right? Up to 4, what do you call it? Yeah, each of these, basically what I'm trying to say is each of these inner elements can have up to 4 elements. That is correct, Matthew. Okay. Yeah, so this is just like a crazy, crazy example of a multi-dimensional array. Let's go to something. So let's talk about how we might populate an array, right? We'll come back up to here. So cool, I have created an array and I want to, I'm just gonna write a very basic, actually, I'm not gonna do that. We're just gonna create a random integer, whatever the random integer ends up being. So I'm just gonna write a for loop that goes over how I'm basically gonna populate this array with a bunch of random integers, right? For int, I'll say r as for rows and columns, just so it's easier for you guys to read the code. R is less than my 2D array dot length. Now, one thing important to note, again, going back to the concept that a multidimensional array is arrays within arrays, when we query this, we're querying the outermost array. So we're only getting the length for the outermost array, which is 3. And that's going to become relevant here in just a second. Columns equals 0. So if this gets me, if this just queries the outermost array, how do we query the next level array? How do you guys think we could do that?
Nested.
Well, we're already nesting the for loop, but, oh, you mean the nested, what would that look like? Type it in the chat. So if I wanted to get the dimension of the inner array, which is 4, how might I do that? Exactly. My 2D array. And you can even hard code this and just make it 0, because all of the inner ones are going to have the same exact they're going to have the same exact length. But this is how you do it. Oh, whoops. C is less than that. So the reason why this works is, and again, it could work for R. You could have R in here. It doesn't, you know, we always know that R is going to be within the length of columns. Or you can make it 0 because all of the lengths are going to be exactly the same. All the lengths for all these rows are going to be exactly the same, even if they don't use all the elements. So we say this first element, which is index 0, grab its length, which is 4. And inside we'll just say, so how do we put a value? We have R and C. What does R and C refer to here? Anthony, doesn't really matter. I always put 0, but I've never had anyone correct me on it. I've seen other people put 0. It doesn't really matter. People are going to know what you mean as soon as they see that anyways. So how do I want to put a value. I'm going to generate a new integer. Int random is equal to new random next int. So we have a random integer here. How do I put random into my array? How am I going to put this into my array? Yeah, exactly. Anthony, why don't you unmute yourself and tell us a little bit about that code that you just wrote and just see if you can describe it to the class.
Well, basically, like you're going into the 0th row, and then you're going to whatever the column is. So in this case, it would be the 0th column for the first iteration, and then you're storing that random int that you initialized above that, and then storing it in there. So, like for the first time, it would be the 0th row for the 0th column, and then the next loop would be for the 0th row for the first column, and then goes on until it's done.
Good. And actually, this is something I didn't do for the other class, but I'll probably link this slot to them as well. But we're going to do a really quick exercise, and hopefully this will be a good exercise for use of the debugger. So we're going to run the debugger, and it's going to stop when we get to here, so we can see our data over here and how it's created. So we have our my2D array here, and we can see all the rows and columns. Right now, everything is initialized to 0 because newer versions of Java make it so that when you declare a variable, but don't initialize it, it defaults to some 0 value for it, whatever is defined in the compiler to be the 0 value. It's bad practice to rely on this. It's better to assume that when you declare a variable with no value, that it's going to be initialized to null. It's better to think that way because not every language has this, and you never know what version your customer is going to be running. They might be running an older version that doesn't assume that this is 0, that assumes that an uninitialized value is null, because that's technically what it is. So if anyone has questions on that, just ask me, and I will break it down a little bit more. But, okay, so we see our array over here. I'm just going to collapse this for now. Other interesting things that we want to take note of is our R and C values. So as we start hopping over, we can start tracking R. So our R counter is at 0. Our Z counter is at 0. We created some random integer over here. And now we're going to put it into my array at R equals 0, C equals 0. So this is the R is equal to 0, and this is column C is equal to 0. So if we skip to the next line, look at that. That random integer we had just made is now in there. Then next, we're still within the inner for loop because we haven't fulfilled this condition yet. So we see now that C has gone from 0 to 1. Then we go generate a new random, which is here. And then we put that right here. The new random went into the 0, 1. And we're going to keep going. And as we keep stepping through, you guys see that we've got the first column all filled. So now C is equal to 3. And then array, my2D array 0 length is equal to 4. So if we increment C again, C would be 4, which would fail this condition. So now we're going to break out of the loop. And we break out of this loop, and then we go back to here, and we're going to increment R. R has now become 1, which means we are now in this next row of arrays. And I'm just going to skip through. And yeah, we would have had, I hope that was enough to show how to use. Do you guys have a better idea from watching that, how to use the debugger, what you look for in there? Did that help clear it up? I know I didn't like explain so much stuff, but hopefully just seeing me kind of walk through it. Yeah. And that's what you use the debugger for, is to just see your code being built as you build it. So we built this. Now, what we're going to do as a class is we're going to populate a 3D array. So if for a 2D array, we needed to use an embedded for loop that was 2 levels embedded, what kind of a for loop do you guys think we need for a 3-dimensional array?
A 3-level embedded?
Exactly. Because we're going to have the x, the y, and the z. So for int x equals 0, this is less than my 3D array dot length, x plus plus. And for those who don't know why I chose those letters, x, y, and z are 3D coordinates, basically. Z is the z-axis, which is the 3D axis. For int y equals 0, y is less than what? How do we get the second dimension? How do we get the 4? How do we do that?
Yeah, my third array.
My 3D array, and then the 0th index dot length y plus plus for into z equals 0. How do we do it for the innermost one here in the 3D array? How do you guys think we get it? Exactly, Sarah. We're gonna have this dot length z plus plus. So my 3D array x, y, z is equal to new random dot next int. This is just the same thing as we did here, except I'm not assigning it to a variable. I'm just putting it straight in. And if we decide to run this with the debugger, and we come in, we get it. First of all, we can actually see, look, our 2D array is completely initialized, which is awesome. Now we're going to watch for our 3D array. So x is 0, y is 0, z is 0. At 0, 0, 0, we're going to put a random variable. If we pop this open, x, y, z, and so on and so forth goes on with the rest of our program. Is this practical to use? Yeah, because that is true. This has a big O of O to the n cubed. The reason why it's O to the n cubed is that actually, I'm not going to go into big O notation. That's going to just confuse the hell out of a lot of people. Is this practical? From a speed performance perspective, not necessarily. But this is typically how you would. We have a completely empty array and we're just initializing it. I'm sure there's more efficient algorithms that you can use. Like you can probably just do this with one loop, and by performing some integer math, you can dump it into, like for instance, if we, no, recursion is even less efficient. Recursion is the most inefficient method of iteration you could use. Iteration is always better than recursion. So if we take this, and let's say we were to convert this from XY coordinates to just 1 through 9. Yeah, good, you should. Recursion sucks. Recursion is so inefficient. So this would be 1. Suppose we have like coordinates 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? This is just us numbering the numbering 0 through, actually I'm going to put it into, let's go back to the whiteboard for this, right? So let's clear this. Suppose we have a 2D array that's 3 rows, 1, 2, 3, by 4 columns, 1, 2, 3, and 4. So this would be 0, 0, 0. Actually, I'll just write the 0, 1, 2, 0, 1, 2, 3, right? I'm not sure what you're talking about there. I mean, you're talking about getting for the Z length. I mean, you could do that, but there's no difference between doing that and hard coding a 0, because all of your arrays are going to have the same length. So it doesn't matter which location you pull them at. It's just fast. It's just exactly the same. One is not necessarily better than the other. They are equal. So if we break it down this way, and instead we number it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we know that we have row, the value of R is 3, because this is a 3 by 4 table. How would we, given, if a user just gives us 0, how do we get the coordinates 0, 0? So our goal is to convert just the flat number 0 into coordinates 0, 0, right? So we need to calculate, and I'm just going to name these things different. I'm just going to name them x and y, okay? For now, we'll call them x and y coordinates, but we know they refer to the row and column. So given just the flat number 0, how can I calculate these coordinates? How would I find the r and the c is kind of the problem we're posed with. Actually, a better example might be to use, let's say we use 7, actually. Let me erase these. So we're going to use, oops, I need to go back to the pen. We're going to use 7. And 7's coordinates are 1, 3, right? Or technically it's y and x, because this is the y and this is the x. So it will be 1 through 3. How would we convert? Yeah, so what we're aiming to do here is rather than having an embedded loop that's going to exponentially increase with whatever the size of our array is, it is possible to populate, oh, and actually this would be a good demo to show too, just in terms of making things more efficient. This is not something you need to think about at you guys' level, but it'll make you, it's going to make you seem really smart when you know this stuff. Y and x. So we had previously talked about that it seems like depending on how many dimensions an array has, we saw that the pattern was the easiest way to do this is however many dimensions an array has defines how many loop levels of a loop there are going to be, right? Or
Why?
Is that part? No, you're good. You're good. Is that making sense though? You guys know where you guys saw this in the example we just had, right? Where the more levels of an array we had, the more levels of a loop we need to have. But the problem is each time we have an embedded for loop, our runtime, our speed exponentially decreases. So it's called the big O notation. This is how we define how many, like what the speed is. And ideally, the fastest speed, it's not always achievable, but it's O of 1. Or sorry, O of n is, I believe, O of n is the ideal speed, because that means however many operations there are, it's linearly going to increase with speed. Whereas if we had like O to the n squared, the n squared looks kind of like, the graph looks like that. So let's say over here is the time, and this is the number of operations. O to the n factorial is the best speed. Yeah, is the worst case. Thank you. Yeah, O to the n is the worst case, but linear or exponential is not that much better. So this is not ideal because let's say this is our operations and this is time. So the linear O to the n's graph, which is the ideal case, looks like that. You can see how for like some arbitrary number of operations, let's say here, you can see how O to the n squared takes more time than O to the n. Is that concept kind of making sense? I know this is like really, really advanced stuff beyond what you guys are getting used to now, but I kind of wanted to just, I'm getting caught on a tangent. If you guys are getting like, if you want me to abort, just click the no button and I'll stop and I'll go back to a basic example. But I'm hoping that like these, do you guys want me to keep going with this? Give me a yes or no on the board. No, AJ, so what this means is for some number of operations, so let me redraw this a little bit bigger. Where's my eraser? Okay. Big O notation tells us how much time it will take to fulfill your operations. And it shows it in a relational manner. So rather than giving you, oh, it's going to take this number of seconds or whatever, instead we have it tell us, based on n operations, it's going to take this kind of time. The most ideal speed is O to the n, which means for each operation, there is a constant time that it takes to do it. So if we draw a graph over here, or on the y-axis is time elapsed, time it took to do it. And over here is ops. That's the number of operations we have to do. In the ideal scenario with O to the n, it's a linear graph, right? For each number of operations, our time elapsed goes up that much. Now, if we look at what O to the n looks like, whoops, that's not what I want to do. If we look at O to the n, it's exponential, meaning the time, let me just double check to make sure I'm doing the right exponential graph. Exponential graph. Yeah. So exponential graph looks like this. For fewer operations, it's okay, but we very quickly get to a point, there is a breaking point where it's slower than linearly. So for smaller volumes, it's okay. But when we get to more operations, it's very, like the more operations we add, the more quickly our runtime climbs up. Whereas this linear method just stays the same because it's constant. So for every level of for loop that you have, you actually multiply. So if we look at this O to the n, so one for loop is O to the n being however many iterations of this loop you have. But then for each iteration of this, you have to do n more iterations here. Suppose like each of these for loops has n iterations. Then this becomes a multiplicative relationship, right? Because this for loop is going to run n times n number of times. That's going to be the max number of iterations. And then the last for loop is yet again another multiplication, right? Because for each iteration of this, we run n times here, and then we run n times here. So when we multiply like that, we get n cubed. So this speed here is O to the n cubed. O to the 1 would basically be infinitely skimming the x-axis. Yeah, O to the 1 is like super fast. And log n is another one that's yeah, best case scenario as well. Log n is better for when you have more operations to do. What does 1 represent? 1 just, oh, this is where like, it's hard explaining this because so much of this stuff is just higher level like math stuff. And when you don't have that background, for me, it's really hard for me to describe this stuff because this is like basic calculus relational stuff for me. Don't be sorry, it's okay. I just mean like I have a hard time explaining it. O to the 1 is just a constant speed. No matter how many operations you have, it's that constant speed. Your speed, like O to the 1, but actually, sorry, I could just draw it on the board. So let's say O to the 1 is in pink. O to the 1 would look like this, meaning no matter how many operations you add to this thing, it's always going to be that same speed. It's technically impossible to achieve, and it's practically impossible to achieve unless you're talking about like the runtime of a single command in Java. But like the runtime of a single operation, like a math operation, 2 plus 3, or like n plus y, that's always going to have an O to the 1 speed for that one command. But you never, in practicality, it never comes about. Anyways, so there is a way to not have to do this, to not have to do this. You don't need to have as many for loops for as many levels of an array. You can actually do it all in a single level for loop. And the way you do that is you number, actually, you know what, instead of like asking you guys, maybe I'll go through it and then I can answer questions, is you number this thing in this manner. So if we look at 7, there's 2 operations that are of interest. So if we get 7 modulo 3, what does that give us? What does 7 modulo 3 give us? Yeah, 1. And if we go 7 divided by 3, what does that give us in integer math? 2, exactly. That's not how that was supposed to go. Hold on a second, guys. One moment. Hold on, I gotta reference some code I wrote. Actually, no, it won't work like this. Sorry, the basis was off. I'm gonna clear all this stuff out. So I know what I did wrong. So let's go back to our 2D array. That's 3 rows by 4 columns. 1, 2, 3, 4. So 0, 1, 2. God damn it, I drew it in reverse. How many columns by this many rows? 0, 1, 2, 0, 1, 2, 3. And then instead of 0 to whatever, we actually go 1 to whatever. 2, 3, and I'll show you why here in a second. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so let's look at this right here. And R is equal to 3, C is equal to 4. Now, I have to double check my notes here real quick. Yeah, okay. So if we look at 8, oh wait, that might not work for non-squares. Oh my God, okay, I fucked this up. Oh, this won't work when it's not square. Oh, and I thought I was gonna be so smart. I just realized something right now. The example I drew out was not gonna work unless if the thing's not a square. What I'm trying to do is there is a way to do integer math so that the modulo of this, so if we have our like coordinates, the modulo gives you the row and then the division gives you the column. But it doesn't work if the matrix isn't square. So let's go to an example where we have a square matrix. So we'll just go 3 by 3. Okay. And it doesn't matter if we number it 0 to 9, 0 to 8, or 1 to 9. But we'll just use the example of 1, 2, 3, 4, 5. I'm so mad. I thought I was going to be like so fucking smart. I need to work on the solution some more so that it works for non-square. Oh, there is actually a way to do it if it's not square, but I don't want to. I might do that after the class is over. We can work through it together for those of you who are interested in looking through that. Okay, so if we take 6, let's say, right? And what would so within our array, 6 is in 1 tube, right? 6, my array 1, 2, here is equal to 6. Okay, so we know R is equal to, R and C are both equal to 3. Oh, I'm really mad. Okay, actually it would have worked for the fucking, I'm so irritated right now. This is the problem with doing shit live. I'm so tilted. Okay, it actually would work for the non-square, and we'll go over it here in just a second. So to get the row, what if we go, what is 6 modulo R minus, or no, sorry. What is, this would be, have to be whatever number we use here, 6 minus 1 modulo R. What does that give us, first of all? So 5 modulo R, where R is 3. What does this give us? 2, yep. And if we go 6 minus 1 over C, this worked in my implementation. Why isn't it working here right now? Anyway, 6 minus 1 divided by 3 is, what's that going to give us? 2. Or no, it's going to give us 1. Right? 1. It is working here, yeah. So, and I actually mix these around. This should actually be and these aren't modulos either. These are, that's a division. So we see we automatically see a relationship between numbering our array 1 or 0 to whatever, right? There's some very simple math that maps our coordinates, right? So if we divide it by the number of rows that our array has, we get 1, or we get the row index. If we divide it by the number of columns it has, we get 2. Let me keep going through with this, and just to show you what I mean. So let's take a rectangular one. Let's go back to the 3 by 4, right? So this is 1, and we go all the way to 12, right? 1, 2, 3, etc., all the way up to 12. Let's take this column over here, which would be 1, 2, 3, 4, 5, 6. This is 6. And we take the same relationship for it again. So 6 minus 1 divided by R, and 6 minus 1 1, 2, it will be 7. 1, 2, 3, 4, 5, 6, 7, 8. Excuse me, it will be 8. These are 8s. Oh, I'm so messy today. Is everyone following along, or are you guys totally fucking lost? Give me a yes or no. Yes if you're following, no if you're totally lost. What I'm trying to establish here is that, well, I'm gonna grab some water real quick. Brain left the room 8 minutes ago. Okay. You can always watch this back later. This is like a really long answer to the question of how do we make our code more efficient? So if we have an array, with some number of rows and some number of columns, right? The convention was that we would have to have, if we wanted to populate or print this array, we would have to have embedded for loops where the number of embedded for loops would have to be equal to the number of rows in our two-dimensional array. And this, sorry. That's not what I meant to say. We have an array of some number of dimensions, right? Let's just say like however many dimensions this is, right? We can have an array of many, many dimensions. And all this means is that there are arrays within arrays. Everybody good so far? Give me a thumbs up if you're good so far. On the participants list, give me a thumbs up if you guys are good so far. Okay. Now, if we want to print or populate this array, we were saying, hey, we would probably need a number of for loops equal to the number of arrays. to the number of dimensions in the array. So suppose our array has n dimensions, then we're going to have that many for loops, that many embedded for loops. Embedded for loops reduce efficiency because for each number of for loop here, actually I'm going to name this something different than n. Let's call it x. We have x number of dimensions. We have x dimensions in this array. For each dimension with the big O notation, we're going to have another embedded for loop, which is going to increase our big O notation by that much. So let's say we have a 6-dimensional array. Then that would mean, let's say x is equal to 6, meaning there's a 6-dimensional array. Our big O notation, meaning our efficiency, or speed, whatever metric you want to call it, our speed for this is going to be O to the n to the 6, which is not great. Again, going back to the graphs I drew earlier, where we compare the linear graph, which is one of the fastest, most efficient graphs, to these exponential ones, which are slower, what that's telling us is the more operations we have to do, the slower our program is going to run. The more time it's going to take, meaning the slower and less efficient our program will be. Give me a thumbs up if you're clear up to now. Clap if you're kind of sort of getting it, and thumbs down if you didn't understand that part. Okay. Cool. I'm glad I still got you guys. So let's think about how we can have an array of, we're going to start with a 2-dimensional array, but we'll change it up later. We'll just do a 2-dimensional array because that's going to be the easiest one. It's going to get very, very complicated very quickly if we go multi-dimensional arrays. So instead of having multiple embedded for loops for a 2-dimensional array, so instead of having a 2-level embedded for loop to print out this multi-dimensional array that I have here, so 1, 0, 1, 2 are the rows, 0, 1, 2, 3. So instead of having to have an inner one, an outer loop that goes through each row and an inner one that goes through each column, there is a way that I can write a loop that will print out that I can just have it in 1-level for loop, meaning we get to keep O to the n as our speed. And the way I do that is I do some math with modulo and division. So we're going to pretend that our 2-dimensional array is actually a 1-dimensional array. We're going to treat it as a 1-dimensional array. And I'm going to take a random index from this 1-dimensional array, and I'm just going to, excuse me, and I'm going to try to convert it into this notation. So if we look at this, we're going to say, we'll just call it a 1-dimensional array A. So this is A7. How do I convert this to A is 1, 3? Everybody understand that part? That's the problem we're trying to solve. You guys with me so far? Yeah, use the thumb. Whenever I ask, just use the thumbs up because I really need a gauge of everyone who's listening and paying attention. Yeah, so the initial problem that we face is if we have a 2-dimensional array, we're going to have to write a embedded for loop, which is not very efficient. It increases the runtime of our program, which we don't want. What time is this class? What time does this class go to? Because before I get into this, it might be, I still need to cover 1:40. Okay. Sure, let's finish this up quickly now. You actually don't need to know it. Sorry, I got super carried away. Let me go over what you guys have to do, and those of you who want to leave can leave. Those of you who want to see the solution to that problem, I'm going to keep doing it. All you have to do for next week is Chapter 8 lab. Chapter 8 lab is the 2-dimensional arrays lab, and all you have to make for that is a tic-tac-toe game on a 3x3 board. I have my sample output here. Everybody knows how tic-tac-toe works. You don't have to use my implementation of how I did this. You could ask the user to give you an like on this board, give you like the indices 0, 1 or 1, 2 or like whatever it is. You don't have to do it the same way that I did, but you just have to make a tic-tac-toe game. For extra credit, you can earn up to 20 points of extra credit on this assignment if you write a tic-tac-toe game that can work for any size square board. So you'll have to just assume that there's a variable board size and write your implementation according to that. It's not going to be easy because it is way easier to just assume you have a 3-size board and write an implementation for that. And that will get you good marks. But if you want extra credit, you can try to tackle this problem. And this is a interview question that a lot of tech companies use. So I guarantee you, you can find the answer to this somewhere online. Just a matter of searching it. But I encourage you guys to try and just draw out the problem on your own first and think about it. And then the only other thing you have to do is, this is your pre-lab. You have to do this quiz. It's like 5 questions. There's 3 multiple choice, or sorry, it's 6 questions, 4 multiple choice, 2 free answer coding. You have 3 attempts, no time limits for each attempt. Just get it done by class next week. And that's it. Those are the only 2 things you have to do. And then next week we'll talk about your milestone 2. Okay. That's it, by the way. If you guys don't have any questions about the homework, you are free to leave. I'm going to go jump back to that multi-dimensional array problem. So if you want to see that, you are welcome to stick around. Otherwise, you can head out for the day. And have a good weekend, y'all. Okay. So let's kind of do... Oh, what's up?
Professor, I have a question about the assignment, the milestone assignment. Have you done with the milestone assignment, have you done to correct all of them?
I don't understand your question. I'm sorry.
Oh.
Oh, is your question about milestone 1?
Yes.
What about it?
Are you asking if you corrected it?
Yeah.
No, I haven't graded those yet, no.
Oh, okay. Thank you.
I'm going to be grading those this weekend. I'm trying to catch up on all the other grading to do. Okay. So the initial problem we're trying to tackle, and I'll keep a log up here. Initial problem. In a 2D array, to print, populate it, we need nested, 2-level nested for loop. 2-level nested for loop is big O n squared, which is less ideal than O to the n, or big O n, which is the speed of a single level for loop. Can we print populate a 2D array using only a single level for loop? This is the problem that we're trying to solve. Cool? Make sense? Give me a thumbs up if that makes sense so far. Or a thumbs down if you don't get it, or clap if you want more clarification on it. Okay, so that is a problem we're trying to solve. So what I'm saying is, here, we're going to pretend that, we're going to pretend here that this 2-dimensional array is actually a single-dimensional array. That's this right here. So we can number this 0 to 11 because this 3x4 array is actually just a single dimension. So it's numbered 0 to 11. Now, because if it's just a single-dimensional array, if we just think of it as a single-dimensional array, then that is how we can achieve the O to the n speed for the loop. But then with a single dimensional index, how do we convert it to be the RC index? The answer to this solution, or the answer to this problem is we use integer math. So I'm going to call this I, So if we just take I, and then we say I modulo R, that will give us, and I'm going to call these X and Y, that will give us X. I divided by C gives us Y. And we'll prove that, and we're going to use a couple of examples to prove that. So if we take 7, excuse me. If we take 7, and we'll do the math down here, 7 modulo R is 3. What does that give us? What does 7 modulo 3 give? 1. And if we go 7 divided by 4, what does that give us? 1. Why didn't that work? So maybe this doesn't work for... Does this not work for rectangles? Non-square ones then? So we're trying to get 0, 3. That would be the case if we were numbering 1 through 12, Stanley. Because this solution works if it's square. Let's do that one first, actually. So just erase all of this real quick. So this definitely works when it's square. And I might have to sit and plan out how we can use it if it's not square. So 0, 1, 2. Let's switch the blue pen. 1, 2, 3, 4, 5, 6, 7, 8. So if we were to take this into a single dimensional array, A of 5, and we want to convert that to A of 1, 2. And then if we do the math here, 5 modulo R is equal, or 5 modulo 3 is equal to 2. I mix these up.
Where are you getting the 3 from?
This is a 3 by 3 array, right? The 2-dimensional one. So R is equal to 3, C is equal to 3. These are the 2 dimensions of it. And then if we go 5 divided by 3, so 5 modulo 3 is equal to 2. 5 modulo 3 is equal to 1. So this gives us that. This gives us that. And this is true if it's square. I gotta fix these. X, Y. So now let's look at an example where I'm gonna just move this. I'm gonna delete this part up here. I'll erase that so I can make some space. And if there's any of you in the chat who are like seeing the solution that I'm not seeing, definitely shout out clues and tips so we can move in the right direction. So let's say we have a 3 by 4. 1. And we know this works because if we did it for like say 7, let's just go back here real quick. So if we did it for 7, oops, 7. So 7 modulo, or 7 divided by R is equal to 2. And 7 modulo C is equal to 1, which is the coordinates of that. So yes, that does indeed become A to 1. Fun thing about mathematics, mathematical proofs, if you establish a rule, you can have a test case and then your test case plus 1. And if it works for both those cases, you can conclude that it'll work for all cases. That is a fun little theory of mathematics that you guys will get into as you get into discrete math, which is induction, exactly. Proofs by induction. Thank you, Juvenal. I know the things, I just never remember the names. Okay, so here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's look at this one. So if we say, so R is equal to 3, C is equal to 4 in this circumstance. So if we say 7 modulo C, we get 3. If we say 7 divided by R is equal to 2. And that doesn't work. We expect that to be 2 minus 1. So where does that minus 1 come from? And let's test it for here as well if it's the same relationship. So 11 modulo C would be 3. So that is correct. 11 divided by R is equal to 2. No. Yeah, 2. Did I do math wrong somewhere? Huh. Did I do math wrong somewhere? Whoever's following along, who's able to follow along, give me a thumbs up in the board if you're following along and you're also seeing like where I see the problem to be.
I'm trying to figure it out on pen and paper as well, so I'll let you know.
Yeah. Oh, so the math is fine. Would it work for here? There's a minus 1 that comes in from somewhere, and I'm just trying to figure out where that minus 1 is from. Let's see if it. Hold on. I'm gonna delete all this. Is that cool? Okay. Let's draw back our array over here. 0, 1, 2, 0, 1, 2, 3. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll look at these first. I'll have this be purple. And the proposed rule is that the index, or we'll call it I, the one-dimensional index modulo C is equal to the Y, and then index divided by rho is equal to the X, where A, X, Y, and in this case, R is equal to 3, C is equal to 4. So we're doing the red one, 3 divided by 3 is equal to 1. 3 modulo 4 is equal to 3. And with the pink, 7 divided by 3 is equal to 2. Seven modulo 4 is equal to oh, I think I know. I'm gonna have to test this as well. Then 11 divided by 3 is equal to 3.
Shouldn't that be 2, not 3?
No, because the closest we can get to 11 with the 3 is 9, right?
Oh, yeah. Never mind. Yeah, I was thinking modulus. Sorry.
Yeah, so for the modulo, you are right. It is going to be 2. Or is going to be 3. 3, 3. Okay, I think I figured it out. So there's this condition of where R is greater than C or R is less than C. If they're equal, this rule works perfectly. This is, so we'll say this is if R is equal to C. If R is greater than C, then this stays the same. Actually, let's go back to green because we're writing the rules in green. I modulo C is equal to Y, but I divided by R minus C minus R is equal to the X. And then the inverse of that is true if the number of rows is less than the number of columns. So I modulo C minus R minus C is equal to Y. And then I divided by R is equal to X. So if this is indeed the case, then this condition, so in the example over here that we're looking at, let's say brown. So this over here is our brown instance, right? That's our brown example, which means we should test an array that's like this to make sure it's true, right? Because for all of these situations, C minus R, the difference between the number of rows and number of columns is 1. So that's where that hidden -1 comes from, is from this right here. So if we subtract 1 from all of these, we actually get what we expect, 0, 3, 1, 3, and 2, 3, right? Everybody follow me in the chat?
Yep.
Cool. So let's test it for if there's more rows than there are columns. Or sorry, the brown was this one, where there's less rows in the columns. So let's test this other one. So we'll say 0, 1, 2, 3, 0, 1, 2, and we'll number all these 0 through 12, or 0 through 11, excuse me, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And once again, we're going to test, we'll just test 3 for now. We'll test that. We'll test that. Then we'll test that. And we're going to be using this rule here in the purple. So for the red, oh my God, I wrote this all thing out of order. So delete that. R is less than C. R is greater than C. So this is what we tested over here. And now that is what we're testing over here. So if we go to red, and this is the one we want to be using, we go to red, I is 2 modulo, or C is
3.
3, yep, sorry, 2 modulo 3 minus R minus 3, in which case R is 4 minus 3 is equal to 2 modulo 3 gives us 2 minus 1 now. That doesn't work. So maybe it's just, this is just a special case if there's more columns than there are rows, because 2 modulo 3 gives us 2, which is what we expect, and then 2 divided by 4 gives us 0. Now we go to the purple case, let's say. 6 modulo 3 gives us 0. 6 divided by 3 gives us 2. So the row is giving us the expected consistently, but the column isn't. Then there's this other weird relationship. And if we did it for the 5, oh no, I'm just stupid. This is supposed to be an 8, not a 6. Toy. 0, 2 is what is expected. Yeah. So if we get 6, that is correct. So if we do 8 modulo 3 is equal to 2 for the column, and that is the right column. And for the row, 6 divided by 3, which gives us 2, which is also what we expect. So this rule is not true. The only special case seems to be when R is less than the number of columns. Or yeah, when there's fewer rows than columns. Interesting. Let's see if that holds up. So we don't need this anymore. These are the only two cases. These are the only two cases that we have to worry about. So let's assume deleting all this. What about 11? We can test that as well. So let's do the case for 11, where we had a row is equal to 4, column is equal to 3. So for 11 modulo 3, that gives us 2. And then 11 divided by 3 gives us 3. To 0. Yeah, so that gives us the right answer. So this is R less than C is the only special case we have to worry about, which is good. That makes the rule easier to write. By the way, class is over. If you guys need to leave, go ahead and leave. I'm just going to keep working on this, and this will be on YouTube, or this will be on the iLearn, so you will be able to watch through this. But if you do have to leave, I understand. Go ahead and hop out. I'm just going to do a really quick example where I try to test this using my code. So I want to do one final test. I want to say row is more than columns, but it's more than by 1. And same thing for the row is less than the column. So let's say we have 1, 0, 1, 2, 3, 4, which means we have 5 rows, and we'll stick with we'll just stick with 3 columns. 0, 1, 2. And because we're just working with the ends, we'll do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So we're going to be using this rule because there's more rows than columns. And let's check for this. So 5 modulo 3 is 2, okay. And then 5 divided by 5 is equal to 1. Okay. Have a good weekend, everyone. I'm actually going to put this, there's a faster way to do this. Let's go back to IntelliJ. And we're going to do this with code. So this is I personally find stuff like this really fun to do in code. I know not everyone likes theory and math stuff, but math theory. If you guys find it fun, I am glad. If you guys don't, that's cool too. So I want to test my rule that I just came up with. Public static void main string args. And we're going to say we have a oh, excuse me. We have an array of should I say we have an array for Java. I'm just going to live code. If you guys have questions, feel free to shout it out. But just live coding for now. And I equals 0, I is less than int array is equal to new int. I'll say we'll just say 15. I is less than array dot length plus plus array at I is equal to I. So we have populated a test array over here. And I'm just going to name it test array. And we're going to have a 2-dimensional array. Actually, it should be over here. 2-dimensional array named my 2D array is equal to new int, and we'll say 5 by 3. So R is equal to my 2D array length, and C is equal to my 2D array 0 length. And in a similar loop, we're going to say int I equals 0, or for each, I'll just do it for each I in test array. I use the bathroom, I'll be right back. Okay, for each in our test array, let's say int random, we're just going to make a random integer, new random, next int, I'm going to say let's say if R is less than C, and then else, because those are our two cases we have to worry about. Int x is equal to R or I divided by R, and then minus C minus R, and int y is equal to I modulo C, I modulo C. Actually, we should do that. Int x, y. All right, later, Anthony. And for now, just base case, I'll do it there, but 0. Else x is equal to I divided by R, y is equal to I modulo C. And actually, what I'm going to do is I'm going to make a new method here. Static int populate 2D array int test array so that we don't have to change the variable names around. Where is it? Let's see. Actually, I'll pass R and C in here. Int R and C. And populate 2D array. Pass in the test array, then R and C. So my 2D array is equal to whatever value we get back from that. Okay. And then we'll have another method called static void print 2D array int array print 2D array 2D array. All right. Return is equal to new int R and C. 3 x y is equal to random image that we created, and then after we're done with all this, we're going to return our array that we created. And over here, we're using the same exact loop. Using a similar loop. Should have a method called static int flatten 2D array int array name 3 is equal to int, which is going to be array dot length times array 0 dot length. Or no, hold on a second. Actually, don't need to flatten it. Let's go back to print. Static void, print to the array. Or int I equals 0. I is less than array dot length times array 0 dot length. I plus plus. And then, just for simplicity's sake, I'm going to say int int r is equal to array dot length. C is equal to array 0 dot length. Out. Int item is equal to array int item x 0 y equals 0. If r is less than c, else x is equal to r, y is equal to I modulo c. Same thing over here. Then I say item is equal to array x and y. If y equal to array 0 length. I'm going to print out a new line. We'll see why that is here in a second. And then system out print item and then a space afterwards. When we run this, oh, -1. Oops. One, two, three. Yep, we get a 3 by 5 array, or 5 by 3 array. Awesome. That is exactly what we expected. And actually, what I'm going to do instead of a space, I'm going to do a tab. That way it's nice. It has some nice even columns. Okay. Yep, awesome. Okay, For those of you who are still in the chat, raise your hand if you're still here, if you're actually here and watching. And if you're not, that's fine. I'm still going to explain what I'm doing. Okay, let's go over all this code that I wrote. We actually have a solution now of how we can print out a 2D array of any size, I believe. Let's just give this a try where this is 3 by 5, and let's see if it'll print out correctly. 3 rows by 5 columns. Ah ha ha ha! Nope. We run into an issue. And x minus 2 is out of bounds. 53. So let's debug this shit. And like I said, if you guys do have to leave, or if you're getting bored or whatever, you can leave. I totally understand. I'm just going to put this up on YouTube later. Okay. So we got 3 by 5. That's why it's 0. I is 0. Oh, we hadn't considered that. Yeah, that gives us a negative, and if this is 1, or minus c, or c minus r is minus 2, and this is if this was at I is equal to 1. You know, we want to get 0, 0, not negative 2, 0. Yeah, you're good, Petra. It's fine. Yeah, no problem. Joe, I'm just going to do some math real quick here. So if we do 0, cello 4, 0 divided by 3. This is 0. This is 4. Right now, this is just 0 because there's no left over. If we go to 1 modulo 4, it's 1 divided by 3 is equal to 0. So this minus 1 only comes into play when we're here at the final at the final row, or the final column. For 1, 2 modulo 4 is 2. Those are all fine. 2 divided by 3 is 1. Or 2 divided by 3 is still 0. 3 divided by 3 is 1. 4 divided by 3 is 1. 5 divided by 3 is 1. 6 divided by 3 is 2. Oh, so this is kind of the boundary that throws it off. I really feel like I should just turn off the video and work on this problem on my own offline and then share with you guys, because this video is just going to go on forever. So I'm going to stop the recording.